Imagine walking up to a vending machine, pressing C4 for a bag of chips, and watching a live goldfish tumble into the tray. You press C4 again, and out comes a spark plug. In a snack machine, that's a mildly confusing afternoon. But in a banking network processing transactions or a security protocol verifying passwords, that kind of unpredictable behavior causes immediate systemic failure. Reliability requires absolute order. When you provide a specific input, you must be guaranteed one specific predictable output every single time. To guarantee that predictability, mathematicians rely on a strict logical structure called a function. A mathematical function operates as an uncompromising set of rules. It is designed to eliminate ambiguity and guarantee that your inputs always lead exactly where they are supposed to. At its core, a function is an architecture that links two entirely separate sets of data together. We start with set X, which we call the domain. Think of this as all your possible inputs, the buttons on our vending machine. Then we have a second group, set Y, known as the codomain. These are all the possible outputs you could receive, the snacks waiting inside the machine. To qualify as a true function, this system has to follow two strict golden rules. Rule number 1, every single element in the domain must be connected to an element in the codomain. You cannot have dead inputs that go nowhere. Rule number 2, no single element in the domain can point to more than one element in the codomain. Pressing one button and getting two entirely different results is mathematically forbidden. By rigorously enforcing these two rules, math creates a perfectly mapped environment where ambiguity cannot exist. This diagram shows a formal mathematical model of a mapping. Let's test it to see if it qualifies as a true function. First, verify Rule 1. Every letter in set X, A, B, and C, has an active connection. Next, Rule 2. No single letter branches to multiple numbers. Notice a key nuance. Inputs A and B both connect to the exact same output, the number 2. This is perfectly legal. Multiple inputs leading to the same output maintains complete predictability. It's like two different buttons on our vending machine, both dispensing the same popular candy bar. The machine is still doing exactly what it's told. In standard math notation, we translate these visual arrow paths into ordered pairs. For this function, our pairs are A, 2, B, 2, and C, 4. Whether drawn as arrows or written as coordinate pairs, a validated function represents unshakable logical integrity. There is a critical distinction between the codomain and the range. The codomain is everything that is possible in set Y, numbers 1 through 4, but the range is just 2 and 4. The range consists exclusively of the outputs that actually receive a successful input connection. Let's shift our focus to the algebraic equations governing modern engineering and programming. This document shows a standard formal algebraic function, f of x equals 2x minus 3. This rule operates across the infinite set of all real numbers. It processes forward with total reliability. Inputting a specific number rapidly computes a specific output. Because the rules of a function are perfectly reliable, we can use them to work backward from an output to discover its exact origin. This is how we find the inverse image. Let's walk through that reverse process. Look at question 3. If we know the final output is 1, we add 3, divide by 2, and deduce the original input was 2. Whether it's a server matching a user to a secure password or a smart thermostat reading a temperature to trigger an AC unit, mathematical functions provide the logical basis for our technology. By locking specific inputs to specific outputs, they guarantee our data-driven world remains orderly and traceable.